So I work for ITRS. What do we do in ITRS? Sorry. We do this, we build this real-time monitoring system for the finance industry. A real-time monitoring system is about data collection at the scale. It is about real-time. It is about setting rules in a rule engine to trigger alerts. These alerts are shown or displayed in these dashboards or consoles or dashboards where the operators can check and take action if things go wrong with their systems, their infrastructure, their applications, okay? That's what we do. And in a way, I like to compare it to the human nervous system. We're pretty good at collecting data, like the human senses. We have this middleware, which is the spinal cord, and we have our rule engine, which is sort of the midbrain, which is taking these fast decisions about maintaining temperature and posture, and if something goes wrong, it can trigger alerts like pain, and we can correct them, okay? But the story today begins 4 years ago when we were pretty aware that we needed to evolve. We needed to do something better. We needed to be smarter while monitoring because we needed to do this. We needed to be able to make real-time decisions based on historical wisdom. The key point here is historical wisdom. For building historical wisdom, you need first of all, you need memory, a good memory, and you need a brain. You need analytic capability. So, as I showed you before, we were lacking a proper, powerful, higher brain. And we went for that. 4 years ago, we checked how can we build this higher brain, this big data brain. We checked the open source technologies and projects, and we decided they were not mature enough. So we started this system, all-in-one system integrated by ourselves, built by ourselves, and we called it Velo. This was our big data engine. Velo was built on 3 core principles. Or the key points of it were, first of all, it wanted to be very simple to deploy. Simple to deploy by using a single process that was to be deployed in a symmetrical peer-to-peer cluster architecture. The second point it does, and this was very cool, it seamlessly integrated real-time and historical analytics. And the third point was, did I forget the third point? It was pioneering, trying to pioneer bringing the computation to where the data is. At that time, it was a new thing. Sadly, finally, last summer we had to cancel or finish the project. And even when we started ahead of all the other projects, of other open source projects, we couldn't keep up with open source projects. So finally, we had to finish this. Then we sort of reflected, recapitulated what we have learned, and we decided that then the open source projects were mature enough to put them together and assemble our brain, our big data brain. And what we did is finally we resorted to Mapa, which was going to wrap all these open source projects with his product in a single bundle. So we went back to this so we could bring back this simplicity of deployment plus extended features that they build upon these open source technologies, and then they respect these open source standards. So this is where we are here now. This is what we are good doing at. So we learned a lot from building this Velo project. And today, I will be sharing what we learned in data visualizations. Forgot to say, there are two ways to build this historical wisdom I was talking about, 2 ways. The first one is human-driven. For that, we need to extract information from our big data systems, extract it, display as visualizations, data visualizations, and feed those visualizations to humans who can make decisions and then take some action back into the system we are monitoring. And the second one is we get rid of the humans some point in the future, and then we have our machine learning, artificial intelligence processes that are extracting information and making decisions by their own. These are the two ways. So I will be talking about the human part, data visualizations, things that we learned. Joel is going to be talking about how to build scalable modeling, which is the robot part, okay? So here we go. 6 things that we learned while building big data visualizations. First thing, big data visualizations is not a matter, is not a task for front-end. This may seem obvious, but it's not. So you shouldn't build a system like thinking I have my backend, this distributed scalable system, and then I process data, and then I cool things with the data, and then I fire it as a cannonball to my front-end developers. I don't do that. Why? Because visualizing data is important, probably is the most important thing until we get robots everywhere, machine learning everywhere, because otherwise you're not building systems for humans, and because visualizing data is difficult, it's tricky, but the most important part, the most hard part of visualizing data should be taken by the most powerful part of your system, which is the scalable distributed backend, okay? So we have to change our mentality and go for this collaborative playing between the backend and the front end. So this is a badminton thing. More on that later. Second thing we learned about karaoke visualizations. In the beginning, I thought I would call these Kappa visualizations for the Kappa architecture, but I think Kappa karaoke visualizations is a better name for it. And the thing is, have you ever thought how cool it is that audio systems can play recorded music or live music the same? Probably you haven't, because you expect it, you take it for granted. But this is not the way we have been doing things with data visualizations. Not only because we would like to have the same visualization, the same charts, and the same system working exactly the same for historical data and for real-time data, but also because we would like to be able to overlay real-time data, over recorded historical data as we do in recording studios. And yeah, we learned with this project, we learned how to do that, and to think always charts are for both real-time and historical. Third thing, probably the most important thing, data visualization is about information extraction. Information extraction. Maybe you have heard about data reduction. Forget about it. That's like data imputation. We don't want to get rid of data. We want to extract important things, the information. So what we do is we have our big data, we extract information from it, and we send only information from the backend to the front end. Information is lightweight, always lightweight, because it's related to our cognitive processes. Humans are all the time applying attention, and we deal with low amounts of information. So please don't do this with your visualization, and this is very common. We take our canon, which is our backend infrastructure, our distributed backend, and we start firing data to our front end, and this grid is an HTML canvas, so brittle, and we start firing, and then after that, in the aftermath, we see the trail, the data left, and we try to extract information for that. This is a very artistic way of extracting information. It's like Pollock's style, but it is not a very smart or efficient way of extracting information. On the other hand, what we have to do is we have to start getting familiar with visualization that are aimed to visualize information, not visualizing data. So for instance, if you're a fan of scatter plotting, okay, forget about it. Scatter plotting is a bad option. It's much better if you can extract control lines and heat maps, but much, much better if you could cluster your data and then you could extract the centroids and the standard deviation ellipses of your points, and then you visualize only that. And if you have outliers, you can overlay the outliers, and that's very light, and you can send that to the front end. You have more examples like these. You have, for instance, box plots are wonderful. Use box plots. There are 5 or 6 values for a box plot, and they show a lot of information. All the information you need is much better than histograms. And at the same time, sequences of box plots are much better than line charts, much, much better. So it's clear that we have to extract information. How do we do that? Is it difficult? Do we need complex processes like machine learning algorithms, like clustering or something like that? Well, luckily, most of the time, we need a quite familiar query to build most of the analytic charts we use on a daily basis. I'm going to show this. This is the only piece of code I'm going to show because we are supposed to come to the Geo on the Beach for inspiration, to have fun, to connect with people, not to see code, but please bear with me. This is the code I'm going to show. This is a very familiar query, a group by clause followed by a select aggregation function. Yeah, I hope you're familiar with this. I give you some seconds to process it. This is our Alembic. I would say the universal Alembic. It serves for almost everything, not for everything, for almost everything. So the thing is the output, this query is processing events that come to our stream, and the output is a limited set of groups with associated values. And with this set of groups, we can build most of the visualizations, the charts we need. I won't prove this now, but in 3 slides, we will have an interlude, and there are several charts there, and you can see one by one the output of this query, how it corresponds to the charts we are displaying there, okay, in 3 slides. Next thing, how do we implement this in our distributed backend? So let's assume, I will show you how, it's easy. Let's assume you have your distributed backend based on a log-based system like Kafka, for instance. Your log is receiving streams, then you implement this query simply like an online streaming process, which is being fed by this stream of events. And at the output, he is classifying by some keys, one key or several keys. The process is dispatching the different groups, and whenever a new event comes for a group, it recalculates or improves or overrides the old value for that group with a new value, a new improved value. And we discard the older values. So we mark as valid only the last value for each group. And that's it. This is our our extraction process working. So this was the 3rd thing we learned. The 4th thing we learned is we have to hold the state. Hold the state is we need to be supportive with the front end. We have to be cooperative. So what we do here is the output of the extraction process, the groups and the values. We right away, after this process, we store them in memory. We store them in memory, in the kind of memory we have around our clusters or whatever. This is a materialized view, simply a materialized view. And it turns out that if we group by several keys, and we have 3 keys in this case, and for each key of the grouping, we coincidentally have only 3 groups, we have this beautiful shape of a Rubik's Cube. Inside every box of the Rubik's Cube, we have an aggregate value, or several aggregate values. That's cool because we can store more than one thing in each pigeonhole, in each box. And we could have simple things like averages, the average, the count, or maybe we can have complex structure like a t-digest structure so that we can summarize statistical distributions. And that's it. The cube, it behaves like a mutable structure. Whenever we have new events, some box in the cube is going to be changed, to be improved. The value is going to change a little, okay? So here we come with the interlude. This is about t-shirts. Depending on the shape and the size of our state, of our mutable state, of our materialized view, we can support different kinds of charts. If we group by no dimension, we have a single value. This is the first case. Then we can hold there. In the back end, we hold the value we need to visualize a KPI in the front end. If we have a small state, only 2 dimensions or 3 dimensions with only a few groups, we can visualize charts that they can fit all the values in the state in a single screen. And then you can do the exercise I told you before. See how each element in the chart corresponds to a single box in the state. 9 boxes, 9 columns. Then we have the long size. It is the long size, not the large size. It's long size because there's one dimension which is predominant. And this is the case for time series. And the time is the long dimension there. So it is good for depicting, for drawing time series. And lastly, when we have a few dimensions and a lot of groups, we can back this kind of visualization where we don't show every single element, we don't show everything because we cannot show it. But what we do is select only a few, normally by sorting and limiting, and we show only a few of them. So this is about holding the state. The fifth thing we learned is after we have our state, our materialized view, we have to deliver the state to the front end. But the good thing is that now what we have in the back end is light, and we can deliver it. So we will have the small sizes of the state. What we do is establish this request and response mechanism with the front end, and we deliver the whole state, and the whole state is light, and we can store it in memory in our front end, and we can visualize it easily with the 3JS or something like that, even vectorial things, right? If we have the big case, we have the big cube with a lot of groups, what we do is we need to put an index in front of it. So when the request of the front end comes, it says sort by this key, and we deliver only an end of the index, only one end, the upper end, the lower end, a section of the index. So we only display in the front end a selection of groups of values, okay? I didn't say, but you can set up this reactive channel to inform about changes in real time, the new values you get in your state. You can reactively transmit them to the front end through this reactive channel. You can subscribe to it. And finally, if you have the long state, the time series, it is cool because you need an index by time. You need to index it by time. And then in the front end, you're requesting only sections of the state, and you can navigate it. And you are asking only for a section, and you can go back in time and forth in time. You get the section. And the cool thing here is that you can subscribe only to the last time bucket with the reactive channels, so you can be feeding the last time bucket, which is the only which is being updated in real time. Okay. Final thing we learned that we need to have a few more steps to build our pipeline for visualizing big data. So what we are missing, the main thing is there, the information extraction is there. We need to put a join step at the beginning, which is we receive our streams, but probably we need to join the events with metadata we have stored around our system, the databases. So we do this join. Then we might want to enrich our events in our stream, so we add new fields to each event. That's enriching. Imagine labeling by cluster or something like that. We add new fields. Then we can filter, because we don't want to show all the events, or we are not interested in all the events. And this is what supports things like dashboards that support cross-filtering. Finally, we feed that into the information structure. Then after that, we have our materialized view, is where we hold in memory the values we want to display. Then we put an index, because probably we need it. And then we put this service that delivers the very light information to the front end. So we have a very light flow of information to the front end. In the front end, we have our charts, and we display our chart. But in turn, our chart has configuration controls, And each control is sending control information to the backend to each single step in the process. So we close the loop, sending information, light information, to the front end, and from the front end, this is sort of the idea of the badminton thing, the cooperative way of building the system, and that's it. That's the 6 things we learned. We think that they are the essence of how to visualize big data, the way to go. Coming back to the idea of the 2 ways for extracting wisdom from historical data, I talked to you about the visualization path to enlightening, and then Joel, thank you, he's going to talk about how to build better scalable modeling and machine learning pipelines.
That's it. Great. Thanks very much. Okay. So part 2, just for those who weren't in the room when we started, my name's Joel Brunger. I'm a system engineer from Mapa, so I don't claim to be a data scientist in any shape or form, but I get to wrestle with some of the models and some of the data pipelines that these guys deal with on a daily basis. Do we have any data scientists in the room? Good. So this might resonate with a few of you. If not, I'm giving you some tidbits of what's going to come down the line, because everybody at the end of the day are going to start using machine learning analytics a lot more aggressively as we move on. Now, like I say, I work for Mapa, and just to give you the very quick overview, what Mapa is, a huge scalable data platform. You can think of this almost as a huge Linux system. So anything you can install on Linux, you can install in Mapa. We provide extra capabilities like streaming and a database, but really we're a platform with streaming database. I don't really want to tell you any more about the platform. I want to tell you how about we're using the platform and the methodology that we've come up with, which we're recommending to our customers. So we have quite a few large customers out there, especially in the credit card prevention. So when we talk about fraud with credit cards, we want to be able to prevent that transaction going through rather than prevent it afterwards. And we're doing a lot with smart cars. So video analytics. So it's all about having that brain and being able to do things quickly. So I'm going to introduce you to what we refer to as the rendezvous model. And the rendezvous model was really brought up because when we talk about machine learning, you're going to hear this phrase that 90% of machine learning is about the logistics, and the other 10% is about moaning about the other 90%. Well, not really. It's 90, and the 10% is where you actually do the real work. So if you 5 days a week, you're spending 4 days getting all your data, putting it all together, and then the 5th day, you're probably doing some modeling. So I'm going to introduce you to the first part. So you can see my diagrams are not probably as pleasing as Alvaro's, but this is really a decision response model. So what happens here is you send a request, it gives you a response, nice and easy. And this is how people get started with machine learning. They write a model, so a model can consist of a program of some kind. It could be as simple as an R or a Python program. It could be using something like TensorFlow. It could be anything. But what I refer to this model is basically your logic, your machine learning. So what we do is we ask it something and it will give us a response. Okay, brilliant. But the thing is, if I've got that model and I'm constantly asking it questions, well, what happens if I want to start adding more complex questions? What happens if I want to start changing the model? I'm pretty much dependent on this traditional way of doing things. You know, it's not very scalable, and there's downtime if you want to modify the model. So how do we get around that? So in traditional places, you find that people use a load balancer to feed all their data models. Now, if you're data scientists and you're doing machine learning, you're not going to just do one model. Creating one model is the way that you start. But that's when you've just started, and you've got to maintain that model, you've got to update it all the time. Things change, so therefore you want to make sure that the accuracy of your model is changing with the way that the data is changing. So the model has to be intelligent enough, or you have to be flexible enough to be able to change as you start to see the change in the data. So again, this is what we see a lot of our customers doing. So they've got a load balancer, they're sending data to model 1, data to model 2, data to model 3. Now this is the same data that's being sent to all the models. It's the models that are different. The thing is, is the data that went to the model 1 is going to be slightly different from the data that goes to model 2 or model 3, or there's going to be a latency in there. So when you try to compare these models, it's not going to be very even. And the whole point is when you're doing machine learning, you want to see as much information as possible to understand whether your model is accurate, you want to see how well it's working, and you want to see how long it took. So there's quite a few things that you want to do. So if we think about this, so these could be like credit card fraud algorithms. So I'll punch 1 into 1, 2, then into 1, then into 2, into 3. Well, if I'm checking multiple models, well, I could already have like a couple of milliseconds sort of latency on this one. So what happens is you're slowing things down. And we all know when you start using modern applications now, it's now. I don't want to wait anything. So it's absolutely critical to be quick. So this is where we start to bring in our way of the rendezvous model. So the input, we're not using a load balancer anymore. What we're trying to do is encourage people to use things like streaming technology, Kafka, or Mapa streams. So basically, you can publish and subscribe to your models. So we'll publish all the data. These models will all subscribe, and they'll all get the same data at the same time. Brilliant. That's number 1 fixed. However, once I've got the information, I want to send the results. How do I correlate those results? How do I compare those results? How can I check whether things are working successfully or not? So it still gives me a bit more of a challenge. Now I've got data coming to all my models, feeding all my models at the same time, but I need to work out what's happening with those models and whether they're actually any good or they're a load of rubbish. Whoops. Oh, don't want to steal my thunder there. So this is where we've come in our rendezvous architecture, and this is essentially the main thing. So we've got the data coming in, so we're streaming the data into all our models. You can have as many models as you want. These could be containers. These could be actual just little bits of programs running on your system. It can be anything. So a model is a group. So you could have hundreds of models. And what happens is they all send their scores to another a Kafka streaming bus that punches that into a rendezvous server. And a rendezvous server is what we're coining, it's a bit of intelligence. It basically takes all results of those and works out which is the best one and sends the results back to the user. So now what's happening is we're getting a bit more intelligence. It's a bit like optimization for machine learning. So I can bring in new models into this cluster, but I can also set them at a status where I'm saying, this is just development. So these are production. The first 2 are production, that's development. It means I can run all my parallel models in parallel. However, the scores will be sent to the rendezvous server, but the rendezvous server will ignore the model 3. So if you're starting to introduce more models into your production environment, you can warm them up with this model. You can start to throw them into your machine learning environment and see how it's reacting, and only enable those models when they're starting to yield the results that you think you need, or you think the accuracy. So this is ideally the architecture of the rendezvous model. However, there are challenges over this model. There's nothing to keep this honest. You don't know whether all this information is correct or not. So what happens is we start to need to add a few more variables. So what we're doing here is doing parallelism to machine learning, but we're also introducing and bringing in new models and retiring new models with no downtime. We have to first bring in what we refer to as the decoy. The decoy is like another model that sits there and it records all the inputs. So as a data scientist, if I want to go and have a look to see what the parameters or what the data sets are applied, the decoy is going to record that information so I can historically go back and understand what was happening in that model. So it just looks like a normal model, but it's just bypassing information straight to an archive, which then we can look at later on. So the decoy is quite important. But the real important one is the canary. So in olden days, the miner used to take the canary down the mines, and it was the first warning to whether there was any dangerous gas or anything toxic that was going to harm the person. And this is where we want to bring canary into our model to try and keep everything honest. So as the data's coming in, there's going to be lots of models down here, but the decoy is recording all the activity, so we know what's recording. The canary is actually the last known best model that we've put in there. So we've been running a model for a couple of weeks, we're happy with it, that becomes our Canary. That's our benchmark. So what's happening is we're putting in something that we know works really well, and then we're throwing in loads of new development and trying new different models, new ways of writing those models into the mix. But the rendezvous server is going to be intelligent enough to work out what the scores are and feed it back. Now, this has multiple purposes. Like I say, bringing in new models into your environment, but also if you wanted to do self-optimizing of the models. If I say I've only got half a second or 1 second time frame of what I want to do before I start reacting back to my customer or to my service or my application, I can actually put time limits on these models. So as they come in, I'm running 100 models. After 1 second, only 2 models have given their results. Great, I'll take it. And this whole architecture is designed to basically start throwing the results to you as soon as possible. Because sometimes it's better to have an OK model or an OK type of algorithm giving you some intelligence rather than none at all. So if someone's applying for a credit card and you're looking for that instant, quick risk assessment and you don't get back the model with the information, well, what's the person going to do? Are they going to give them the credit card or not? So the point is you want to have something at least, and that's when we can actually put some timing constraints on. So what we're doing is giving you a methodology of how to approach that machine learning. So we've actually got quite a few customers using this, and they all started off with a decision model, where they were literally just trying to run one model, but how do you upgrade it? How do you bring another model into the mix and keep that one running? So this has been deployed most places, but the point is one of our customers, again with the credit card, with the fraud, they can't have any downtime. They've been running their system for 4 years, constantly up, no downtime at all, but they've been changing their models all the time, they've been changing machine learning. All they do is throw the model into the environment, give it a development status. We're not going to take any notice. We compare the results. We do our own intelligence from a data science perspective, saying, OK, that one looks ready to go. I'd change the status to production, and off it goes. And it's in the mix, and it's starting to provide and yield some results. Now, I've kept this really high level because I didn't want to go right down to the bits and bytes about what exactly each component's doing, so I've tried to keep this completely high level. So really, this then came down to why did ITRS want to partner with Mapa?
Okay, yeah. Yeah, this comes back to the what do we get from Mapa? As I said, first of all, we wanted to bring back this simplicity of deployment. We want it always to have. Real time is critical because we do monitoring from the beginning. We needed it to be real time. Again, the idea that the processing has to be in the back end, as we need for data visualizations, and for the added features, enterprise features they provide us with. So that with that, can you go to the next one? So in summary, with them we can build this smarter monitoring we need to build. That's the idea, right? You have other things there. The global data fabric and support this very interesting thing, support machine learning in real time. But that's it, yeah.
Yeah, we also got a few other things in there. Like the one requirement is if you're a global organization, sometimes you might need a global data fabric, and that's where you can actually see your data, although it might be physically located in multiple clusters. So the idea was absolutely flexible, nice smart monitoring, but really be able to do real-time monitoring in machine learning. And that's becoming more and more critical because obviously propensity, engaging people while they're actually using applications, or they're doing some tasks, especially like retail. If they're on the website, you want to deal with them there and then. If you're dealing with gambling or betting websites, if someone's losing, you want to maybe try and keep them on the application from running away. So again, it's all about propensity and real time. And
so, can you, yeah, thank you very much. Sorry. We are right out of the room. Thank you. If you have questions after that, along today and tomorrow, we are right out of this room. You can come, and we will be delighted to talk. Thank you.
Absolutely. I'll give you the finer detail.
Thank you.
We can hear you clearly. We can also repeat the question for you.
So how do you actually test the models and the result themselves? Like quality processes there and when you're developing? I mean, I'm sure you're not going to push it to production.
No, and that was the whole point of where we went back to the rendezvous server. So the rendezvous server is essentially a bit like it's just a program in itself, which is there to extract information and log it, and maybe push that into a database. So it records all the information into a log file or an audit file, and that's where then the data scientist can have a look at that log file and see basically what the scoring is from that model. We all know that when you write a model, that all the other models doing the similar activity shouldn't deviate too much for them to be quite accurate. So what we're trying to do is compare for likeness when we've actually run the whole model through. So that's why we have recommend that they have a status of whether you're in development. You label it as a development or pre-production, and they're warming up the models, so they're running in parallel with the live ones, but they're not actually being used until you're happy with the results that are being provided to you. So there is a whole bunch of metrics that's being thrown out for a data scientist to analyze, to understand on how those models are performing.
Is there an automated process to do that?
No, this is really a methodology. So this is what we're trying to promote. We've got a book out at the moment called The Logistics of Machine Learning, where we introduce this one, and then the next phase of that book will actually be to actually tell people how to do it in detail. So it's a methodology at the moment, but it will be productized at some point.
Yes, so about the models, which is the criteria parameter to decide, let's create any model, is accuracy or is latency? So how do you decide to
That's exactly what I missed out from my talk, so thanks very much for mentioning that. So the reason why you would want to introduce more models is because you may find a different way of technique of actually writing those models that give you much quicker response times or better accuracy with those models. When you write a model, that's not it. You've just started the journey. How do you manage that model? How do you make sure it's always performing right? Because if you're actually betting your business on these models, they've got to be accurate, otherwise all of a sudden you could nosedive the company and you're responsible and you're the next one in the news saying how you've taken down a company. So the idea of this is a very safe way of getting people involved with model management, but absolutely everybody's got to constantly evolving those models, and we're trying to do it in a very safe and realistic way.
Yeah.
Another question is the input data that you put, it goes to each model. Which is the criteria to decide to which model it goes? Is randomly, or do you have any prediction to decide, let's put the data in model 1 or in model 2, which is the criteria to decide which model it goes?
So you're asking about the input. So this input coming in here, what's defined in that input and how does that marry to the models? So really, this input's going to be core business data that you've already done some analytics over or machine learning to understand on what data that you want to put through a real-time feed in order to model. All those models will receive exactly the same data, and that's the whole point of it. So I might run multiple rendezvous architectures on my platform. So this could be for fraud, I could have another one for risk, I could have another one. So the inputs, the data inputs are always going to be the same. It's the models that are going to be different so that you can actually make sure that they're being managed in a way.
So you decide randomly. I mean, you need to put the data in just one model, or you distribute it in all the models?
Yes, so this is the idea. This is a streaming technology. So, yeah, absolutely. These all subscribe to the data at the same time. So the thing is, you might only have one model, But you might, as you evolve and you're bringing in other data sets from around the business, or there's other requirements to try and improve that model, or you find that it's going out of whack slightly, you'll keep adding more and more models. So, the models in this architecture are really all related to a single use case or, a specific solution at that time. So you run multiple platforms. Right. So the question I was asking then, when you get a certain pattern, how can you sort of leverage or highlight which model would be most optimal for that? Now, we wouldn't really take that approach so much. What we'd probably do is maybe put like a time limit and look for an accuracy and really put down the logic in the rendezvous server from the scores coming across. So, like I said, if this was for fraud and I wanted to do something in very quick time, I might say, in here, anything that hasn't given me my results back within half a second, discount them. And then I'll take the best one from there. But if it's not happy with what it's got, you can always relate back to the Canary, providing the Canary has given his results. So the thing is don't forget, we're trying to put a few other sort of models within the mix to keep it honest. Decoy, so we can record all the information. Canary, because basically that's our baseline. We want to make sure that everything is very similar to that Canary. Hello.
Hi. Right at the beginning of your slides, you mentioned a few cloud service providers, like AWS, Azure. Is there anyone in particular that's quite suited to implementing what you're describing, the model you're describing?
Healthcare?
Sorry?
Did you say healthcare?
No. I said right at the beginning, those cloud service providers like AWS,
Right.
Azure.
Yes.
Are there any platforms that you would recommend to suited to?
Oh. So the question is, we mentioned that we support multiple cloud. There's different vendors. Which one would we recommend? Which one is potentially better for model management? They're all pretty much the same, because at the end of the day, we're just leveraging system resource and then disk space. So it really comes down to, at the end of the day, if you're doing everything in memory, then it doesn't really matter. It all provide really the same capabilities. But if you're talking about getting persistence from data from storage, well, some might be slightly faster than the other. I'm not going to commit to which one it is. So in other words, there is really no difference, to be honest with you.
Any other questions? I've got one from the anonymous duck. What do you think is going to be the next big thing in machine learning as a service in the coming years?
People want automatic self-service machine learning. People don't want to do it themselves now. They want it to be completely autonomous. So you're getting things like data robot or data accu, where basically you throw a load of data at it and it'll go along and find that data for you. That's what a lot of people want. But whether they'll get that is a different thing. I mean, you'll still need to use a level of intelligence, and the things that we're talking here about models, we haven't even got into whether it's supervised or unsupervised, but really, when it's supervised, this is when the models become a lot more intelligent, a lot quicker. So, going back to that question, which I've just suddenly had a brain fart. What was that again?
It was basically, what do you imagine would be the big trends in machine learning? What's the next?
I think it's trying to be more automatic, more intelligent itself. The applications will just throw some data at it, and it will start to help you accelerate into that fashion. I mean, it's obvious that there's not a lot of data scientists out there in the market at the moment, and everybody's screaming for this capability. So it's about trying to automate analytics, I think, really, at the end of the day. Simplify it. Optimize it.
And the other question I have here is, how do you determine which data is useful for the consumers? Data metrics of the system, for example.
data metrics is useful for a system.
How do you determine which data is useful for the consumers?
It really depends on what data you're being fed in a real-time fashion, or what data is relevant to you. So if I go back to the credit card company, you know, they're throwing through transactions or requests for a new credit card all the time. So it's actually giving me some input that I want to model. So that could be a person, that could be, you know, a premise, it could be a phone number, it could be multiple sort of inputs that it's given me about trying to understand who I am. That would have been inputted from an application, and then it will do the risk assessment in the model. So, you know, applying for a credit card is not the great use case, but when you're actually checking the transaction of a credit card, that's when it becomes valid in a real-time fashion. So you're looking at those transactions, and those transactions will have timestamps, it'll have geolocation information, it'll have a whole host of information that it's going to have within that single stream, a string that will then get processed by the model. So really, the data input is defined by what you're trying to put analytics or machine learning on. So someone must have some data and say, well, there might be value in here, and that's when you use the technique.